Yes, sir.
Yes, sir.
Yeah, thank you. Thank you. Just give me a minute, I will come back. Just 1 minute. Yeah. Thank you. Good evening. Sorry for the small delay.
Thanks, sir. Good evening.
Good evening. So today we'll talk about before going to the energy storing devices like capacitors, that is super capacitors, batteries, like lithium-ion battery, how it works, interarchitecture, also about lead-acid battery. Of course, lead-acid battery still we are using in the old vehicle, but all electric and hybrid vehicle nowadays they start using lithium-ion. That is the latest technology. We'll see that. I told you today I will start with energy storage, but we will start after completing the power electron, which is pending. We just started the 2 classes before. I think somehow I missed MOSFETs. Okay. One of the most important power electron device you will come across here when you talk of electric vehicle or hybrid vehicle, where we call power electronic device as a driver, motor driver circuit, all those things is, as I told you in the previous class, power diodes, power transistors, power MOSFETs, and IGBT. IGBT, nobody talks this one, correct? IGBT, nobody talks as a power. Generally is meant for design for IGBT, which we talked last two classes yesterday also. As I told you that basic divider, diodes, transistor, FET, MOSFETs, all these things are there. One is called small signal devices, small signal amplifier, small signal diode, transistor, MOSFET, or SCR. Again, one more thing we saw SCR. All these are small signal means they only, as I told you, that they work with 0 to 30 or 50 volts maximum, and 0 to 5 amps, less than 5 amps. Worst case, very rarely 10. 10 is they say high current. So these devices which operate 0 to 50 volts and current range of 0 to few amps, milliamps or amps, less than 10 amps something, they are called as small signal devices, because the current harvesting small power devices. Same diode, transistor, MOSFET, if they operate in operating over hundreds of volts and tens of amps or hundreds of amps, and power rating as a kilowatts, megawatts, they are called as power devices. They call it power electronic devices. That's what different. Already told you. Again, we started MOSFET. I wanted to complete the MOSFET today. The full expansion MOSFET is metal oxide semiconductor field effect transistor. Already we talked about field effect, which is called as FET. FET can be used as an amplifier, similar to a transistor. MOSFET can be used as a transistor amplifier. FET can be used as an amplifier. Transistor can be, all three can be used as an amplifier or power drivers. Power driver, they're going to have high current, high voltage, so which will be used for actuating a bigger device like motor, solenoid, which requires kilowatts of power. So MOSFET is prefixed with another three words: metal oxide semiconductor. If you take the first letter alone, is called as MOSFETs. We'll see what a MOSFET is. Already I told you, but anyhow, let me start fresh quickly. We'll go through. No issue today. We can complete. MOSFET is similar to a FET. It is called a field effect transistor. It has three terminals. One is called as gate terminal, which is called as input terminal. Then you have a terminal called drain. Other one is called source. Source, drain, base can be equated to base of the transistor, collector of the transistor, or emitter of the transistor. Okay. Again, when we talk about MOSFETs, there are two types of MOSFET. One is called N-channel MOSFET, other one is P-channel MOSFET. Okay, we'll see one by one. Before going digging deeper inside the working of the MOSFETs, we'll see what a primary feature of a MOSFET compared to FET. In previous class, we talked about FET, if you remember. Anyhow, but then I told MOSFET is an extension of field effect transistor. It has additional one layer, which is called as insulating layer or silicon dioxide layer. Okay, so MOSFET has additional insulation layer made of silicon dioxide layer, which is deposited above the gate terminal. Correct? Gate terminal will be taken from a metal, conducting metal. Below that, there is an insulator. So the insulator actually separates the gate metal deposition. Please see the figure here. The black color one, this is the metal deposition, black color, metal contact for gate terminal. Please see the gate terminal coming out. It is connected to a metal deposited, in which is shown here, metal deposition or contact. And this metal is deposited over a silicon layer. So this is my silicon layer. I can actually, it is gray color for you to understand. I am painting with red color. This layer is called as silicon dioxide layer. You can see here, this is silicon dioxide layer. This layer is deposited over. This is the N plus is called as source of the MOSFET. Another N plus is called as the drain of the MOSFET. And below that, there is a P substrate. Basically, when we say this one, First, we take a P substrate, a rectangular block, correct? Which is made of P-type material. That is called a base material or substrate. This is long way used in FET and MOSFET. So the main, to take a P substrate on which you dig a well, 2 wells, fill it with N plus. That is heavily doped N region. N is N-type material. P means P-type, where positive charges is the majority carrier. Okay. In N, you have electrons, negative carriers. Okay. So you dig 2 wells in the P substrate, deposit with N-type semiconductor material. Okay. So that also heavily doped. Plus means heavily doped. That means more electrons are there. Generally, you may ask, sir, what do you mean by N and N plus? Correct? I say N means N-type material, it has electrons. N plus means what? N plus means, for example, if I say N material, for a given volume of this semiconductor material, as I told yesterday, there are 1,000, originally before doping the impurity or phosphorus in the silicon material, there were 1,000 atoms in given volume. I displaced 100 atoms with the phosphorus atom. So it became a N-type material because phosphorus atom has electrons in the outer orbit, extra electron outer orbit. So it provides charged particles, which is electron, which is negatively moving. Please note that the electrons are free, not attached to any atom. So they will move inside the N material randomly. But if electrons are moving randomly, there is net current is 0, because electron should move in one direction from location, one location, another location, some direction, correct? Is flowing. If electrons are moving randomly, they cancel each other, net current is 0. Okay, that is the one thing. So in the P-type material, you have holes and they are also randomly moving, because I added impurity aluminum in silicon. Out of 1,000 atoms of your silicon, pure silicon, I removed 100 atoms, added 100 aluminum atom. So aluminum positive holes. So that means they are also random moving as long as you don't give external power. The holes in the P-type material, electrons in the N-type material moving randomly inside your N-type material. So there's no current flow. Only when I give external power, they force the electron to move from one direction. Generally, positive side, we say that electrons are moving from negative to positive side of the battery. We are coming power, correct? So we say current is flowing from positive to negative. It is called conventional current. That's okay, fine. The whole idea what we are talking here, how the MOSFET works, that's what I told you. It has a P substrate on which 2 wells are created, which is filled with N plus heavily doped. This one, they form drain and source of the MOSFET. And then in between, you can see here the P substrate is here. This area is nothing but a P substrate only. I am painting. Correct. So this whole area is also yellow color. This is also actually the P material. Okay. P material, one more thing you have to remember. In P material, I said the majority carrier. In semiconductor, they call 2 things. One is called majority carrier. Other one is called minority carrier. If I take P-type material, majority carriers are plus, that is holes. Okay. Everywhere, I told you there are, if you add 100 aluminum atoms inside the silicon of 1,000 replacing this one, 100 holes will be there. They form majority carrier. But there will be some electrons also. Randomly few electrons compared to holes. 100 holes are there. There may be 10 or 5 electrons per given 1 mm cubic. Generally, we talk millions or billions. But understand why I said 100. Few electrons are there. These electrons are called as minority carrier. Electrons are minority carrier in case of P material. What is majority carrier? Holes. because there are more number of holes. If 100 holes are there may be 10 or 5 electrons, which is called minority carrier. That's why it is called a p-type material, even though there are few electrons, but they are there, you remember. Similarly, if you take n-type substrate, correct, n-type material, the majority carriers are electrons. Everywhere electrons are there. I said 100 electrons. I have doped p phosphorus 100 atoms, replacing 100 silicon atom out of 1000 atoms. So my n-type material has electrons as the majority carrier, because I have doped, added phosphorus, but it will also have few holes here and there. Holes are called as minority carrier. Holes are minority carrier, note down, minority carrier in case of n-type material. So these two things you have to remember. That is an important point as far as MOSFET working is concerned. Okay. Now I told there are two type of MOSFET. One is called N-channel, other is called P-channel MOSFET. Okay. So that means if I say N-channel MOSFET, the main base material is a P material on which two heavily doped N regions are there. They are attached to a metal contact. Wires are come out. Terminals come. One is called source, other one is drain. Then remaining period, you can see that is a cut section view. Remaining area of the P is here. This area, let me show it in the green color. This area on which we deposit the silicon layer, silicon dioxide layer, insulated layer, above which a gate metal deposition is made, from which a connection is made. So between the gate contact, metal contact, and the below the P substrate, there is a insulating layer, silicon layer. This is the speciality of MOSFET, which is not there in case of FET. Okay, I can say that FET can be simply, you can easily understand. This is a FET. I am talking about N-channel FET. P substrate, there will be two wells. There is N plus, again N plus. This will be called a source. This will be called as a drain. Correct. Then I dig one more. This one I get at this one, which is called as a gate. Okay. So now the P substrate and there's a terminal, and we deposit this one gate region. We are deposited a gate region. Okay, that is with supplied with a gate voltage. Okay, so this will be a P-type material. Yeah, this will be P-type. In fact, okay, again when we talk about, before that I'll just clear this. When we talk about FET itself, again you have N-channel as well as P-channel. There are two type of FETs similar to MOSFET, because as I told you, first they invented transistor, after they invented FET, then they invented MOSFET, one after another, because of the to improve the semiconductor engineers or scientists develop new transistors. In FET also you have N-channel MOSFET and also P-channel MOSFET. Okay, so if I say N-channel MOSFET, okay, it is made of N-type material. I have N-type material, a bar, correct, which is made of N-type material, okay, on which there are two P materials will be doped, well as created. Okay, so these two are shorted together. Okay, I am talking cut section. This is called as a gate terminal. Okay, then one end I put a metal deposition. This also metal deposition. This is called a source. This is called as a drain. Okay, across this we supply a voltage. Okay, so gate we give control, VGS control voltage, and because there are one P region, another P region, in between I have N region through which current from this power supply plus, current will go inside the drain and go like this. Current flow happens. Actually, we'll say that the electrons are flowing in reverse direction. Battery minus to the source and enters in this one and comes out and comes. This is the electron flow. We know that current flow is always shown opposite of electron flow. That's why we say current is flowing from battery plus to the drain of the JFET and comes to this one through where this channel. The channel, this is called as channel. So since it is made of N material, it is called N channel FET, JFET, okay, junction with the N channel FET. Instead of that, if we take a P-type material and dig two wells and put N, and this side, there are two sides. This is called a source. I give a voltage like this, plus minus, which we will call VDS, and this is called a drain. This is called a source, and these two things are connected together. Connect to another voltage, which we called as VGS. This is gate voltage, plus minus. This is control input. If I vary the VGS from 0 to 5 volt, this is called a channel. This is called P channel because it is made of P material. The channel is this one. Okay. If we vary the VGS, the current going through this is called IDS. If I vary 0 to 5 volts, gate voltage, IDS will vary 0 to 5 amps. So that is how the FET is working. Please see that in the FET, you don't have the insulating layer. This insulating layer, which is below the gate terminal, correct? This insulating layer is not there. This is a specialty of MOSFET. That's why I said the primary feature of this one is insulation layer, which prevents the current flowing into gate terminal. For example, I give my control voltage like this. Okay. And minus plus this is my VGS. And between the source and drain, I give the main voltage. Of course, there's a load resistor, and this is plus minus, which I call VDS. Now, if I vary this, what will happen? The current flowing through circuit, IDS, will vary. Okay, so my input is VDS, 0 to 5 volts or 0 to 10 volts. The manufacturer says, accordingly, IDS may vary 0 to 10 amps or 0 to 100 amps, depending upon power rating. Okay, you can see here, main thing is in this one, my gate voltage, I am giving control voltage here, this current, which is called a gate current, IG, will be theoretically 0. Why? I am giving a voltage from my control signal that is given to metal, but in between the semiconductor layer, the channel, this is called as a channel. Between the channel and the voltage given to gate, I have insulation layer. Correct? Insulation layer is there. I am showing with the red color. This insulation layer is made of silicon dioxide, which doesn't allow any current flow from my control signal. Please note that I told you this VGS gate control voltage can be a sensor voltage. Correct? Your sensor voltage varies from 0 to 1 volt, 0 to 100 milliamp, or millivolt, something like that. Or it can be from the microcontroller. And there should not, current should not flow inside my gate. Correct? It is called a loading effect. We don't want loading effect. When the sensor voltage provides and my electronic device, whether MOSFET or FET or transistor, where we are giving at the base of the transistor or gate of the FET or gate of the MOSFET. If I give, it should not consume current. Please note that transistor and JFET both will consume current. When I give voltage. Transistor consume more compared to JFET. Okay, so that means transistor has more loading effect. Please know that it cannot be avoided, but still we are using. And JFET has higher input impedance at the gate, so it consumes still less current. If I go to MOSFET is insulated by this layer, thin layer of silicon dioxide. And if I give the input voltage, the metal contact of the gate of the MOSFET, no current can go because this SiO2 or insulator layer prevents. But it induces a channel. That's what we are going to talk about it. So because of that, we say that MOSFET is much better than the JFET. JFET is better than a transistor as per input current consumption or input impedance. We'll say that the Zin of MOSFET is very high. Generally, how much? Very high. 10 power 9 ohms or 10 power 12 ohms also. Correct? That means 10 giga ohm or 1 giga ohm, 5 giga ohm. Correct? It can go to tera ohms also. Very high if the thickness of the insulated layer MOSFET is gate is bigger. What about JFET? For JFET, the input impedance can be in the order of megohms, 1 to 10 megohm. That is 10 power 6 to maybe 10 power 7. Okay. When I come to transistor, Zin of transistor is in the order of kilo ohms to hundreds of kilo, few kilo ohms to hundreds of kilo ohms. So we can say that the MOSFET is much better. That is one of the primary reason for developing the MOSFET from the field of a transistor. Okay. So you got to understand there are two types of this one. N-channel MOSFET. The substrate is made of lightly doped P material. Please note that they call N-channel MOSFET, but the base material or substrate is made of lightly doped P substrate. Okay. That means it has few electrons, minority carriers. Here and there are few minority carriers, more plus. Okay. But main thing in MOSFET working is based on the minority carrier. So they use P-channel substrate on which they created two wells doped with highly doped N plus region. One they call a drain, other one called a source. And above the channel, this is called as channel region. This is called as channel region. Channel region is between the source and drain region. There are two N plus the in-between region, this region is called as channel region. Okay. In the channel region, when gate. Now, this is structure of the N channel, because later when I give appropriate gate and drain source voltage, the minority carriers inside my P substrate will be attracted. They will be attracted and form a thin layer, correct, of pure electrons inside the P substrate. So please note that these electrons are connecting the source terminal with the drain terminal. Okay. So this one provides a conducting path. The accumulated electrons below the gate terminal forms a conducting path. So the current from electrons, I can say that electrons from the source can start moving through this to this one, and basically you are going to connect a voltage source like this. Okay. So then electrons are moving in this direction. I told you the opposite direction is the current flow. This is what we say IDS. Or now if I connect a load resistor RS, then I say that load current is flowing when the channel is formed. To form the channel, what I have to do is I have to supply a positive voltage to the gate. We call VGS. If I give a positive voltage, for example, 0 to 5 volts, if I increase, there will be a current flow from drain to source. So by controlling this VGS, I am controlling IDS, which is called load current. This is how the MOSFET works. Okay. It is similar to JFET, but only difference is the insulating layer, which provides very high input impedance. So the MOSFET is much superior as per the current consumption from the sensor loading effect analyzer, because input impedance is very high. And other attributes also that we'll see. So this is the N channel MOSFET. If it is a P channel MOSFET, again this is P channel MOSFET. Correct? Please note that when I say P channel MOSFET, the substrate is made of N material, lightly doped N material, which has the positive charges, which is called a minority carrier. That means more number of electrons, few number of positive charge, they are randomly distributed inside the N substrate. Now, I have two P wells, correct? One is called a drain, other one is called a source. From that, the black color things are called metal contacts, okay? Through which the P material is connected to metal contact, the terminal is brought out. We call it this. Then again, similar to N channel MOSFET, in P channel also, you have the insulating layer. Insulating layer is there. Above the insulating layer, there's a metal deposition from which gate terminal is taken out. Okay. Now, again, if I bias the voltage properly between the drain and source and gate, then current will start flowing in the channel. A channel will be formed. When I give a voltage, a negative voltage like this, this should be connected to this, and between this and this, I connect my load and this one. This is plus minus. This is VDS, correct? And this is my load resistor. This is plus and minus. Plus is connected to source, and the minus of the VDS connected source, this is become a ground. We call a ground terminal for the P channel MOSFET. Correct? Why it is called P channel MOSFET? The holes, minority carrier of the N substrate will be attracted by the negative voltage what we are applying. This is called VGS. In case of P channel MOSFET, the gate should be supplied with negative voltage. Correct? 0, -1, -2, -3 like that. Then only a current IDS will flow. IDS will flow from my P channel MOSFET to load, and through the battery, it will come like this. Like this, current will flow. Okay. To attract the holes, minority holes in this one, I am applying a negative voltage. Correct? If I apply negative voltage in the gate, the negative voltage will produce an electric field here, which will be minus. Okay. That will attract the minority carriers and come and form a layer, conducting channel. This is called as conducting channel. Okay. So you can see here, this is the conducting channel made of holes from the N substrate. When I give a negative voltage to the okay. So plus minus. So these are there are two types are working. So now you understood there are two types of MOSFETs. One is called N channel, other one is called P channel. Now, before going further, I want to say my MOSFET is shown here. Correct? My MOSFET is shown in the previous page. For example, this is N channel MOSFET. The symbol is this. This is P channel MOSFET. You can see that there's an arrow coming out in case of coming out and reaches the source terminal outwards. That is called a P channel MOSFET. If arrow of the source is like this. Another thing also that you can see that it is some dotted. There are two modes of operation. One is called an enhancement mode, other one is called depletion mode in the MOSFET. That also we will see what it is. And so here symbolically shown, this if I take this N channel MOSFET, what is inside my this one can equivalent circuit. We can say equivalent circuit of MOSFET. It can be shown like this. This is my gate terminal input. This is the ground, power supply ground. This is my gate terminal. This is called as RG, which is nothing but your Zin. And okay, and I give plus here. I am talking about N channel MOSFET. Okay, then internally I have one resistor and one current source. This is called a current source. This is symbol arrow downward or upward arrow, that means current flow shows. And this is my Zout, or sometimes some book R0, output resistance. This is called as RG, or gate input, or gate resistance, which is also this one. And this it will be connected to my external. Plus minus, this is my external power supply. This is my load resistor. So this is my drain terminal. This is my source terminal. Okay, please see here, this part is called as the equivalent circuit of a MOSFET. What it does? One resistance which represents input impedance or gate resistance. Then there's a current source. This is a current source. The current flowing through is nothing but G subscriptum into VGS, where GM is called the conductance of MOSFET. Okay, GM is called current. VGS is the input gate voltage. Input gate to voltage, because we are applying with reference to the source. Common. This is called common source MOSFET. Okay, common source, I am giving input voltage here to the gate terminal with respect to my source. Output is taken across this. This is my output across the load resistance. That's why it is called as common MOS, this one. And this is Zout is in parallel with a current source. How much current? GM. GM is similar to gain. This is called as, a correct name is called transconductance. It is called as transconductance of the MOSFET. This value is decided by the manufacturer. Similar to your beta in case of transistor, current gain, correct? I told you beta of the transistor is decided by doping density of base and emitter collector of a given transistor by the manufacturer. If he wants beta equal to 100, accordingly he will add impurities. How much impurity should be, atoms should be added in the base, collector, emitter region will be decided. Theoretically they compute and actually deposit and find out. So similar current gain in case of transistor. Similar to in MOSFET and FET, we call as GM is called the current gain. Correct? It is actually that is going to decide how much current is flowing through the load or IDS, and that is decided by what you call as transconductance. So this is called as equivalent circuit. Just note down the circuit. Basically what this one, and this is my external. We are giving power supply external. Similarly here we will be giving input voltage VGS from the sensor or from some other circuit. This is my gate terminal, and this is my drain terminal. This is my source terminal. Okay. Now, to go further, I told you there are two types of MOSFET. One is called N-channel MOSFET. Symbolically, again, N-channel MOSFET is further divided into two classifications. Correct? One is called the enhancement mode MOSFET. Other one is called depletion mode. Similarly, if I take a P-channel MOSFET, please think that N-channel is similar to NPN transistor. Correct? P-channel can be considered. It's not exactly, I'm just giving an idea. And PNP, there are two types of resistors. Now, in case of N-channel MOSFET, they can work in two modes. One is called enhancement mode, other one is called depletion mode. Okay, we'll see what it is in subsequent slide. So that means similarly, P-channel MOSFET can work in enhancement mode or depletion mode. How do you know? Correct. If you see a circuit, a power amplifier circuit driving a motor, you have circuit in which circuit means I'm talking about drive, correct? Transistor symbol, correct? If I see this, I know it is a transistor, it is NPN transistor. If we see a transistor, something like this, I know it is a PNP transistor, correct? If I see a diode, I say it is a diode. If I see something like this, I know that it is an SCR. This is a resistor, capacitor, inductors. Like this, you can identify. How will you identify these four? Enhancement mode, N-channel MOSFET, depletion mode, N-channel MOSFET, or enhancement mode, P-channel, or depletion mode, P-channel. How do you find? By seeing this symbol. This is symbol. Please see that. Generally, it may look there. Sometimes they put a circle around this also, like this. Okay. You will see three terminal. Drain is represented by D, source is represented by S, and gate is represented by G. Okay. Now, we take N channel. How will you differentiate enhancement mode MOSFET and depletion mode MOSFET? It's very simple. You can see here, the gate is represented like this, like L, correct? One L. Okay. In the depletion also same L only. Gate is represented by like this. Then they have written gate. Then, if you see the depletion mode, you can see a one straight line coming. From this, there are three lines are going like this. Equally spaced lines, one vertical line, on which right side, you see that two horizontal lines are going. And the bottommost two horizontal lines are shorter. And one arrow is shown here. Right? Then from top, you put a vertical line. I say D. This is drain. Okay. The bottom two lines, the center line with the ingoing arrow, shorter together will be brought out. That is called as source. S means source. D means drain. G means gate. Right? So now you can identify easily. Gate is there. If the drain and source are connected, three lines are connected by a continuous line like this, then and if the arrow is coming inside in the middle line, I know that it is a N-channel MOSFET. The arrow represents, if arrow goes in the source terminal, then I know it is N-channel MOSFET. Then if the line connecting the drain and source is a continuous line, then I know it is a depletion mode. Instead of that, again, the line is broken. There are three horizontal lines. The vertical line is broken into three parts and the arrow is coming in. You can see that this line is broken. 1, 2, 3. And three horizontal lines are there. In the middle line, from right to left, one arrow is shown here. Then these two are shorter. This is called a source. The upper one is called a drain. This is gate. So if I see the discontinuous line connecting the drain and source terminals, then I know the MOSFET is N-channel MOSFET. It is enhancement mode of operation. We'll see what it is in the subsequent slide. Don't worry. Understand. Okay. Similarly for P-type. In P-type, N-type, what is the difference? If you talk about depletion mode, again, gate is like this and continuous vertical line, three horizontal lines. The middle line arrow is coming out. And this is connected to source. Correct? The arrow, the middle line arrow is coming outward. Then it is called a depletion type P-channel MOSFET. Same thing with the discontinuous line, same arrow is coming out, then it is called an enhancement mode of operation. Okay. These are the four types you will identify. Okay. Now, it is called symbolic representation. Constructional view, how it look like P-type and N-type MOSFETs. We are talking N-channel MOSFET, P-channel MOSFET. Similar to what we just now talked about the FET, you take a P substrate. Correct? This is N-channel MOSFET. We are taking a P substrate which has electrons as minority carrier. P material, majority carrier holes. but our main intention is electrons. It has few electrons, which is called minority carrier. How many electrons should be there? That depends upon the pentavalent impurities in the P material. Please say sometimes they add valency or sometimes it can be automatically created. Basically, it is now we take a P substrate, it has electrons and minority carrier. Then what we did do, we dig two wells, correct, on top side and dope with N plus heavy. This is called a heavily doped N region. Heavily doped N region. They are called, one is called as a drain, other one is called as a source. Okay. Now, what did you do? Dig this one, and being a MOSFET, you have to deposit the silicon layer on the top side. Correct? Completely this one, then make a hole through which you deposit with the black color one, which is nothing but this is the metal contact. Black color is not visible when just again repainting with yellow color. Please that from which the voltage is given. It is made a punch through the silicon material above the N plus region. Both the N plus region will be, holes will be made and metal will be deposited. Yellow color I have actually shown is a black original diagram. Yellow color is a metal conducting. From that you take a terminal out, one is drain, other one is a source. And then in the middle region, this is called as the channel region, I told you, right? Between two N plus region, one is drain and a source. Between the region is called as channel area or channel region, which is part of the P substrate. Okay. Now, here you see that nothing is there. Nothing is shown here, but for another. Now, above that, you have the silicon, this one, insulating layer. Then we deposited the gate terminal metal contact. Above the, you can see the maroon color. Maroon color is the insulator. Above that, you metal, this is a metal contact. Gate metal contact. Gate terminal metal contact. Deposited. From the take a terminal, G is represented. Okay. So this is the N channel MOSFET. Okay. What did you do? We took P substrate. Just a few minutes before we talk, if you talk about N channel FET, not MOSFET. N FET. What did it do? We took a N material, then we deposited P. One end, this end is my drain is one, other one is source. These two are together called a gate terminal. Correct? This is a P region. This is a P region. The whole material is N-type material. And the current will flow through this material because this is N material. That's why it's called N channel. But in case of MOSFET, we take a P substrate, dope to N plus region and supply voltage. So a layer is formed between these two. Conducting layer. A conducting layer. A conducting layer formed by electrons. Formed by electrons attracted by the gate voltage. You apply a positive voltage. Okay. So VGS plus minus. If I apply a positive voltage to gate terminal, it will attract these electrons. We correct minority carrier because these electrons will be attracted here. And they come and form a layer. That is called conducting layer. Correct? Conducting layer, if I give you a gate voltage. Okay. So the electron will, how much electron will come and depends upon what is the voltage. If I give 1 volt, maybe 10 electrons. If I give 10 electrons are attracted. If I give 2 volts, 20 electrons are attracted. I give 3 volts, VGS, 30 electrons. So as I increase the gate voltage, more electrons will be attracted, thick layer will form. Thicker the layer, more current can flow from the power supply like this. Correct? This is nothing but IDS, drain to source. Correct? So which is going through my the load resistor. So the drain to source current, which is flowing from the battery into the drain and inside the channel, formed by the gate voltage. If I give positive voltage, more electron from the substrate will be attracted. They come and stick below the gate. Now, this one, but insulating layer. So this through the layer current will flow. This is how MOSFET works. Okay. This I am going to explain slide by slide. Okay. We'll talk about N-channel MOSFET. We are talking about N-channel MOSFET. Similarly, if I talk about P-channel MOSFET, I take N substrate. Okay. Which has N substrate, majority electrons. The holes are minority, few are there. That's what shown here, plus, plus, plus. Randomly, they are there. Now, I applied, again, it has on the N substrate, 2P regions are there. One is called source, heavily doped, P plus. They form drain on this one, and metal contacts are taken out. Then, yeah, again, metal is deposited over the silicon layer. This region is channel region. This is called as channel region, correct? Now, I have not given any voltage here. Again, I have not given any voltage. Do you see any electrons here? The electrons here? No. Correct? Since the gate is not supplied to control voltage, 0 volts, I kept it open. Similarly, in P-channel MOSFET, gate is not supplying any voltage, right? And I have supplied source and drain with a positive voltage. Again, here also, still conduction layer there. Now, if I give a negative voltage, minus plus, this is my VGS. Please see that minus of the control signal VGS is connected to gate, positive is connected to ground. That means if I vary this 0 to, say, for example, minus 5 volts, that means minus 1 volt, minus 2 volts, minus 3 volts, like that. If we increase, as in this, these poles will be attracted, they come and form a layer here below the gate terminal, insulating part. So then the current can flow like this. Correct? Current is flowing because of hole. Correct? Holes are attracted to the form layer. Already P plus region has a holes from which the current from the battery applied negative voltage to the gate terminal of the N-channel MOSFET. This is basic operation. Okay. Any questions, please ask, because it's very important. In the exam, you may be expected to write about this with a drawing, all those things. Definitely the question will be there. Okay.
Sir,
Yeah.
sir, the picture on the right side, these are enhancement mode MOSFETs, right? Not a depletion mode MOSFET.
Yeah, this is enhancement type. Depletion type means it will have built-in layer, this one channel already. While fabrication itself, they will have electrons. The P-type material, this region will be filled with electrons, some material, correct? N-type material, channel will be formed. That will be depletion mode. In enhancement mode, similarly here also plus will be there. Conduction channel will be already pre-formed in case of depletion MOSFET, but in enhancement mode, conduction layer will not be there. But by applying the voltage to gate, appropriate the positive voltage in case of N channel and negative voltage in case of P channel, the minority carriers in the substrate will be attracted and they form the layer. That is called enhancement. Because enhancement means enhancing means increasing. What you are doing by applying more positive voltage to gate or more negative voltage to the gate of this one, I can attract more holes or more electrons and I can form thicker layer. Thicker the layer, more current, IDS, drain to source current, load current will increase. So that means if I give more positive, if I want more current to flow through my load from the drain to source through the channel, I give more VGS, gate voltage. 0 volts, 1 volt, 2 volt, 3 volt, maybe up to 10 volts. If I give, for example, power MOSFET, if I vary VGS, I am talking N channel enhancement mode, this one, VGS vary to 0 to 10 volts, or then the current IDS may vary from 0 to 100 amps. Because the MOSFET is designed for 100 volts. I am mapping, correct? If I give 5 volts, how much will you hear 50 amps current? If I give 1 volt, then 10 amps current will flow. Okay.
Okay, sir. Thank you.
Okay. Now we'll go a little more deeper. Okay. So as I told you, the MOSFET can work in two modes. One is called the depletion mode. Other one is called enhancement mode. In depletion mode of operation, gate to source VGS, voltage applied as this is input. Please note that this is input voltage, which we are going to apply between source and we are talking about common source like common emitter. Must be 0. In depletion mode, correct? If I give 0 volts, then current will freely flow. I'm going to explain. So that's why depletion mode operation is called as normally closed switch. MOSFET can be used as a switch also. You know that MOSFET can be used as amplifier, it can be used as a switch, like a mechanical switch on off. Okay. Many times power electronics, we apply square waves to control the current and voltage, which is called switching mode operation. Very sorry. Which is called a PWM, pulse width modulation. For controlling AC motor, DC motor, all those things will do that. High voltage, this one. So MOSFET can be used as a switch or it can be used as an amplifier also. Please note that transistor, MOSFET, JFET, all this thing can be used as an amplifier as well as switch, depending upon your application. Now, as somebody asked, who was that? Is it Chidambaram? Just now.
Yes, sir. Yes, sir. Yeah.
Yeah. Very good. So in depletion mode, already a conducting channel is available. In depletion mode, even with 0 gate voltage, the current will start. In depletion mode, if the 0 voltage itself, there will be some amount of IDS, load current will flow, because it acts like a closed switch. I am going to show you, I have the figures, I will show in this one. In enhancement mode, only when you apply gate voltage, whether a positive voltage in case of N-channel MOSFET or negative in case of P-channel MOSFET, which works in enhancement mode, current will flow, conduction will happen. Then only when VGS is supplied, then only MOSFET will switch on or switch off. For 0 volts, it won't work. But in case of enhancement mode, depletion mode, at 0 volts, current will be going, some amount of current. If I want to increase more current, what I do? I give more negative voltage. If I want to reduce the current, I give more positive voltage. So that the current from when VGS is 0, for example, 10 amps current is going, control voltage. If I increase plus 5 volts, the current will increase to 20 amps. If I give minus 10 volts, it will become 0. Current will become 0 amps. So from 10 plus or minus, that is the advantage of depletion mode operation. Okay. Again, since there are two modes, depletion mode and enhancement mode, there are two types of MOSFETs, N-channel, P-channel. So there are 4 combinations. N-channel enhancement MOSFET, P-channel enhancement MOSFET, N-channel depletion MOSFET, P-channel depletion MOSFET. There are 4 modes of operation possible from 2 types of MOSFET, P-channel and N-channel. Okay, note down. Now, let us understand how the MOSFET works. I am starting with N-channel MOSFET operation. N-channel MOSFET in enhancement mode. Okay. So the MOSFET can work in 3 modes. One is called off state. Okay. The other one is called as positive conducting state. Okay. Then the third one is on state. Same thing. Whatever we talk. First you have, see, this is the off state. From that, you have to make it working. Current flow, we are talking enhancement mode. That means we need to supply a gate voltage. Gate voltage should be greater than 0. In case of off mode, we can see the gate voltage is 0. We are talking about enhancement mode. Okay. Now, in case of off state, for enhancement mode, N-type, this one, the MOSFET, I have shown, we have, this is the enhancement N-channel MOSFET, correct? P substrate, there are N plus, I can put the 2 N plus, and this is the channel. This region is channel. You see that I have not given any voltage to gate, but I have given a positive voltage to drain and the negative of that to power supply, VDD, correct? Sometimes they put VDS, some books they put VDD. This is voltage given between drain and source. And across this, I can put my load resistor. I have not shown load. I can show the load as a resistor. I connected like this. Please note that my gate voltage left open. That means I have not given any voltage, VDS equals 0. In this case, you see that there are there are no carriers or channel, correct? No channel is formed. This is channel. Channel is formed by, in case of N-channel MOSFET, channel is formed by electrons. Electrons are generally represented by minus sign. Okay, you can see that I have applied positive voltage. For example, this is 100 volts, but VGS equal to 0. I am not connected to any power supply. So you can see that there's no current flow. The layer is not, conduction layer is not, our channel is not formed. Correct? This is first figure. What did I do? Next, I gave this itself. I explained why current is not flowing. I'm explaining. Please note that there's a N plus and a P substrate. So that means, you know, N and P are touching, they are touching each other. This is called as junction. Again, this also, there's a junction. There are two junctions, correct? As a junction is sort of formed between N and P material. If in diode also we know, correct? Diode also we have P and N. There's a junction is formed automatically. Similarly, your MOSFET also it is formed. Correct? It has formed this one. Junction is formed and which prevents the current flowing from the VDD. We know that this is equivalent to, correct? So this is equivalent to one diode. You can see that's what I represent here. Each junction, this is one junction, this is P and again P. P is there. So this is one diode, this is one diode. Okay, we are given voltage like this. What I do? There are two diodes. I say D1 and D2. D1 is formed between source and the base. Correct? Source and the base. Okay. The base are the P material. P material, what is that? It is connected to gate. Correct? We have the deposition. So right now you are not given any voltage, but you are given voltage between these two alone. There are two diodes. This diode is forward bias. Correct? So you can see that you are applying a positive voltage to the cathode of this diode. D2, this is the cathode, this is the anode. Cathode of the diode 2 is connected to positive voltage. Anode is connected to 0 because gate voltage given 0. Here you have your gate, correct? And you are given 0 volts. So that means this is 0 volts. Anode is connected to plus, for example, this is 100 volts. We know that this diode is reverse bias. Correct? That's why I said it is a reverse bias diode. Now, take about this diode, D1. This is 0. This is negative. Correct? This is connected to negative of the bias with respect to gate. Gate, this region is 0 volts. Anode is connected 0 volts. Let me clear it, you will understand. This is 0 volts. This is 0 volts. This is plus 100 volts. This is minus volts, negative voltage. Okay. So what happens? This diode is closed. Right? That means this diode is closed. That is shown as a switch here. Please see here. This is the switch I am showing here. Okay. Switch is closed. The diode is conducted. It will conduct. Correct. Positive voltage is anode connected to 0. This is negative. Compared to 0, negative is this one. So this diode is forward bias. But whatever this diode, this is anode is 0, cathode is plus 100. That means this is reverse bias diode. That's what is mentioned. For understanding, will I return? So this diode is reverse bias. The switch is open. The diode is open. Reverse bias diode is open because it's not conducting. But this diode is, but the voltage is applied between this. Correct? Current has to flow through this diode and go through channel, go through diode like this current. One switch is closed, other switch is open. So even though I have voltage, the current they call IDS will not flow. That's why my MOSFET is not working. When VGS is 0 volts, my N-channel enhancement mode MOSFET is not working. Because current flow, there's no way one diode is open, other only close. Both the diodes should close. Okay. Otherwise, I need to find a magic or create an additional channel through which current can flow. That's what I'm going to do next. What I'm doing, I took to make my this one MOSFET to work. I have to supply, apart from supplying VDS, for example, I told 100 volts, drain is supplied to positive, negative is connected to source. Fantastic. Drain to source is forward bias. Now, I am adding one more power supply, which is called VGS, which is called a control signal. the negative of the second power supply is connected to source, please note that this is it can be a sensor, control signal coming from a sensor. Correct? So now, positive of the sensor or control signal given to gate. Okay? Once I am given this, what happens? Please note that do you remember capacitor? What is a capacitor? Can anybody say? What is a capacitor? Mechatronics, just 3 months before or 4 months before.
Yes, stores energy.
How it is made? What it is made of? Fantastic. What is made of?
Yeah, two plates and
Fantastic. It is made of two conducting plates, two metal plates, correct? Conducting metal plates separated by a dielectric, correct? Or insulator, dielectric or insulator. And this is plate 1, metal plate, other is plate 2, they should not touch. And take 2 ways to form a capacitor, that is, it can store electrical charge. You are 100% correct. Okay. Now, you see here, what is this? This is the metal contact, gate metal contact. Correct? Metal contact. It is like a plate. You deposited. From that, you are taken and given a positive voltage. Okay? What is this P? P is a semiconductor material. It is a conducting material. This metal is a very good conductor. Compared to P material, is a semiconductor. It is not insulated, but still it is a conductor. There is a plate here. There is a plate here. You think that P material is a plate. What is in between? This one. This one. Yellow one I am just marking. Insulator. Correct? In MOSFET, gate metal contact is separated by an insulator from the P-type, N-type material, depending on P-type material. So there are two conducting material separated by a dielectric. So can you think this is a capacitor? It works as a capacitor. MOSFET between the gate and the channel region. Channel region is a P-type material, N-type material. It is still a conductor. It is not insulated. Correct? Two conducting region separated by a pure insulator, which is nothing but a silicon dioxide. Correct? So this forms a capacitor. Okay. Now, if I give a voltage to capacitor, right? I take a capacitor, something like this. I connect my power supply, say VCC, say I give 10 volts. Okay. Initially, this is my capacitor. This is P1, this is P2. I have a switch. And before T equals 0, switch was open. Okay. At T equal to 0, I close my switch. What happens? The electrons will come from the negative terminal, move like this. Electrons are represented minus like this. In battery, who is generating electron? Battery is a power supply. What is supply? Electrical current. Electrical current is nothing but flow of electrons. It can be flow of holes also. In case of semiconductor, P-type semiconductor, it is flow of holes. In N-type material, flow of electrons. In metals, there is no holes business. Correct? In battery, no hole business. It can, later we are going to do, next class we are going to see about batteries. Batteries are generating electrons. Which terminal? Battery has two terminals. Correct? Positive and negative. Negative terminal generates electrons. Okay? Negative terminal only actually generate electrons. Now, if I connect a load resistor like this, the electrons from the negative terminal flows to my load resistor RL. Where it goes? It is attracted by the positive terminal. Correct? It is attracted by positive terminal. It cannot go from negative terminal to positive terminal. In the battery construction like that, from the electrons are generated by the negative terminal of the battery, but they cannot go to positive terminal. They are prevented. Inside battery, there's a mechanism. It prevents. So they will be waiting on the negative terminal. Correct? As I take for a lead acid battery, correct? You have lead. There are two plates, anode and cathode, which will put inside a non-conducting, for example, rubber or a plastic container filled with electrolyte. Correct? H2SO4, diluted H2SO4. Right? Now, if I immerse my anode and cathode electrode inside the diluted sulfuric acid of lead acid battery, immediately chemical reaction happens both at anode and cathode. Anode is called positive terminal, cathode is called negative terminal. In the both the places, the chemical reaction happens and the negative terminal creates electrons. That is what current. Then the electrons will be deposited on the surface of the negative terminal. Even though inside the electron cannot move to positive terminal. The electrolyte prevents them. Okay. So the electrons are created at the negative terminal by the electrode. Generally, it is made of PbO2, correct? And then the electrons will be waiting at the negative terminal. Once I connect my external load, correct? Once I connect my external load, what will happen? This is my external load. Let me use different color. Correct? Once I connect, the electrons which was here will start moving. It finds a path through load resistor comes. It is once I connect, what happens? This positive terminal attracts these electrons. The electrons which is sitting at the negative terminal inside the battery are waiting to reach the positive terminal. Desperate, but it is not allowed to move from negative terminal to positive inside my battery. So they are waiting. Once I connect the external path by connecting resistors, this negative, so they start running. So we say electrons are running, correct? From negative terminal to positive terminal through my load resistor or my switch, correct? So the circuit is closed, continuously happens. The negative terminal generate electrons, those electrons attract to positive terminal. Once they reach the positive terminal, they are neutralized. Again, the negative terminal generates electrons. So as the electrons are generated by negative terminal, through the load, they reach the positive terminal. That's how the power, electric power is generated. Okay. So now,
Sir,
yes, please.
sorry to interrupt, sir.
Yeah.
If a student wants a break for 5 minutes, can we have a break, sir? It means we can ask the students.
Definitely, you should ask. Yeah.
Yeah, sure. Means anyone wants a break, actually?
Yeah. I forgot. I totally forgot because I was thinking. We started late, all those things, so I forgot.
No problem, sir. No problem. Team, anyone means, do you suggest having a 5 minutes break?
Sir, I think we can continue if it's
okay. We will continue.
Okay, sir. We can continue.
Thank you.
Thank you.
Okay. Sorry. You Chidambaram, yourself or anybody can remind me. After 1 hour, anytime you can do. 2 hour class, please remind me. We'll have after 45 minutes, you can have 50 minutes, remind me, so we'll have a break.
Sure, right? Sir. Sure. Thank you.
Thank you. I forgot. Okay. Now there's a capacitor is formed. Okay. Between the gate terminal and the P substrate and separated by the insulating layer. So that means this side we are going to get positive charges. Correct? The capacitor, one plate, the metal plate is connected to the VGS positive terminal. So this will be positive. We know that already P substrate, what it has? Electrons, minority carrier electrons are sitting waiting whether somebody will attract. Correct? Nature is like that. North pole attacks south pole, electrons attack to holes attack this one. So they are waiting. Once you apply the VGS, these fellows are attracted and they start moving here. And they come and deposit themselves here. Okay. So now this is now the electrons are sitting here. Already you have the electrons here inside my N plus region, source and drain. These electrons were waiting for the path. Hey, please give me path. What happened? Already we are given positive voltage to the drain. That means this is positive voltage. I say the 100 volts is here. Source is negative. Correct? These electrons, the electrons here they wanted to go here and go inside the battery and reach here. But there's no channel was available because this region was empty. Correct? This region was empty before I am applying the positive voltage. Now I applied the positive voltage gate. So what happened? As I told you, the electrons come and form the layer. So a conducting channel is created. Conducting channel is created by the supply voltage, this control gate voltage. If gate voltage is 0, no conducting layer, so the current cannot flow. Now that created, so the current start flowing from this terminal, correct? Battery like this, it start flowing. Electrons are flowing like this, current is flowing like this, correct? This is electron flow, negative to positive. Current flow we say positive to negative. So current flow. How much current? So this current is called as IDS. So if I vary my gate voltage from 0 to 5 volts, my IDS may vary 0 to 10 amps or 0 to 100 amps, depending upon current rating. And that current is supplied by this battery. Please note that the current is supplied by this fellow through, because I am connecting my load here. Correct? That's how it works. That is what mentioned in this one. How it, a positive voltage related to the source produces an electric field. That's what I showed, plus here. Maybe red will be better. Okay. The electric field is created because of that. The bottom side, electrons from the P region are attracted. So a capacitor. So this works as an energy storing device. But this path is sufficient for current flow from here to here. Load. That's how the enhancement mode N channel works. Okay. That is on statement. That's what I already explained. A gate capacitor. That means here positive charges will be there because I'm giving a VGS. Already I supplied the voltage. Correct? This N channel with this VDS or VDD. So the current ID goes, IDS is flowing when I vary this voltage. You can see that the minus sign means electrons. Electrons are attracted because of this positive voltage. You can see that this is what. So here you have positive. So the whole thing I call a capacitor. Okay. So if the IDS is proportional to VGS, that's what I said. For the particular MOSFET, they say VGS can be varied from 0 to 10 volts. They say IDS is the output, correct? Is can vary from 0 to 50 amps. That's what I said. IDS is proportional to VDS. If VDS is 0, sorry, VGS is 0, IDS is 0. VDS equal to 10 volts, IDS will be 50 amps. If VDS equal to 5 volts, this will be 25 amps. Proportional, mostly, I'm just saying proportional. So this is called conducting state. That means by varying this voltage, I can change the conduction. Conduction means how many electrons. More positive voltage, the path. I can say that. Here you will have more. So this is the thickness of the path. Correct? So more electrons can go, more current can go from one place to another. Correct? So giving this. So if I want to switch off my MOSFET, what I have in enhancement mode, what I have to do? I have to cut off this voltage. Right? If I make VGS equal to 0 volts, automatically this layer disappears. Conduction layer disappears. If VGS equal to 0, conduction layer automatically disappears. That means there's no current flow. This is how you switch off the MOSFET. Okay. If the gate voltage reduce or return to 0, conducting charge gradually disappears and MOSFET returns to 0 state, original state, no current. Even though VD supply voltage between drain and source, so the control voltage is not there. MOSFET remains off state till you apply the gate voltage. That's it. Okay. So now we want to show how the MOSFET work as a what you call the input-output characteristics. We saw in the transistor last semester. You remember we saw about 0 to 10 volts. For example, VCE. This is 5 volts, and this is my IC collector current. If I supply different base currents, this is IC. So, for example, IB equal to 1 milliamps. This is IB equal to 2 milliamps. IB equal to 3 milliamps. Like this. This is IB equal to 5 milliamps. This is 4 milliamps. So, this is IC. When I apply this, this may be 40 milliamps. Correct? 0 to 40 milliamps. For VCE, this is voltage apply VCE. Correct? For given IB, if I vary this, the current start increasing. This is, I told you, input versus output characteristics of transistor. We saw in this one. Similarly, for MOSFET, again, we have this one. What is the input? VGS. Please see the x-axis 0 to this is 8 volts we are talking. Correct? We are talking 8 volt VGS. Okay. Again, we know the diode. Do you remember diode? In diode, you apply a voltage anode to positive like this. Correct? Plus minus. This is the V supply. This is my ID. Voltage I call it VD. Correct? If I say V supply, if V supply equal to 0.10 volts, what is ID? 0. If this is 0.1 volt, again 0. 0.2, 0. 0.4, 0. 0.69, 0. 0.7 volts, the supply voltage. Immediately, ID becomes some value, not 0. It is not 0. That depends on inside or outer. ID equal to supply voltage divided by RD. RD is the dynamic resistance. Correct? So we need to see that up to 0.7 volts. When V supply is smaller than 0.7 volts, ID, diode current flowing the diode is 0. When V supply equal to or greater than 0.7, ID is not, ID is not 0. How much will be dependent on resistance? Similar to that, in case of MOSFET in enhancement mode also, as the increased voltage from 0, 1, 2, you can see 1, 2 like that, as the increase up to 2 volts, there is no current. ID is 0. There's, even though applying your voltage, correct? Nothing happens. But once voltage exceeds the gate voltage, VGS, correct? Beyond 2 volts, then you can see that IDS is coming. This is, for example, 3 volts. This is for 4. This is for 5. This is for 6 volts. So this is the input control voltage. This is the output, correct? Drain voltage. You can say that this is 1 amps, 2 amps. This I can say 3 amps. I don't know. For example, I'm saying 4 amps. This is 5 amps, correct? But up to 0.2 volts, even if I vary the gate voltage, control voltage, output to current is 0. You can see the current remains 0, right? Current remains 0. Vertically is not moving. So the voltage at which the MOSFET start conducting. What do you mean say conducting? When IDS is greater than 0. Drain to source current is greater than 0. When for a particular VGS, that voltage is called VT, threshold voltage for a MOSFET. Threshold of the MOSFET is decided by the manufacturer. In the data sheet, they will say whether it is 1 volt, 0.5 volt, 2 volts, something. Generally, it will not be 10 under. It will be less than 1 or 2 volts. 0 to, it will not be 0. It will be a 0.1 volt, 0.2. Lesser is better. Better control. But that you have to see the data sheet. Okay. So this talks about input versus output. Current varies. Then this also input also, you can see that I keep my VGS equal to 2 volts input voltage. And I vary my drain to source voltage, just like VCE, which are, VCC varied in case of transistor. 0 to, for example, this is the 100 volts. For this MOSFET, correct? MOSFETs are available up to 500 volts, 1000 volts also. I am varying, correct? This is a 10, 20, like that. I mean, this is 50, increasing. I am keeping gate voltage equal to 2 volts. Please see here 2 volts. You can see that current doesn't go. Vertically, no current happens, correct? So, for 1.2 volts is less than my threshold voltage. That's what is mentioned here. Please see here, VT for this transistor is 2 volts. What voltage I am giving? Correct? I am giving 0.2 volts. That is threshold. That means 0 to 2 volts, where current will not flow. I gave 2 volts, so still current remains 0. So I know that this MOSFET threshold voltage is 2 volts. Now, next what I did, I increased my gate voltage to plus 3 volts because this is N-channel enhancement mode, correct? So that means gate voltage should be a positive voltage. I gave 1 volt, nothing happened. I gave 2 volts, nothing happened. What I do, I gave 2 volts. I increase my drain to source voltage 0, 10 volt, 20 like that increase up to 100 volts, correct? Still no current flow. 2 volts. So I found that 2 volts, once I give slightly greater than 2 volts, current start flowing, but I did not draw here. I took it next to voltage. You can see that the current starting to become flat. So this is called input. ID is output, correct? This is the output. This is the input. This is VGS is the input voltage. I keep input voltage constant. I vary the supply voltage between my load and this one. So the current. So this I understand. Okay. Main important VT threshold voltage is very important, which is like a VB equal to 0.7 volts in case of transistor, diode voltage 0.7, correct? Which is called a cut-in voltage, correct? In case of transistor and in diode, it was called as cut-off or cut-in voltage, correct? Which was VBE equal to 0.7 volts in case of transistor, VD equal to 0.7 volts in diode. That also silicon transistor made of silicon material. Similar to that, if it is a MOSFET which is working, and if it is enhancement board N-type, and any type, N-type, P-type, will have some minimum voltage for which, up to which the current will not increase 0 to 1 volt, 0 to that, whether P channel, N channel, it won't, output will not come. That voltage is called as threshold voltage. That is what is shown here, correct? So input output, remember, in exam, sometimes you try to explain how the N channel MOSFET works, input output characteristics, you need to draw these curves, correct? Because these are hand-drawn only. Correct? Maybe you can do it. Okay. Similarly, now that we saw the N-channel enhancement mode transistor as a MOSFET, similarly, P-channel also possible. Correct? What is the difference between P-channel and N-channel? The substrate material only different. Correct? You can see that P-channel means the substrate material is N-type material. Here you will get positive voltages. And you have to give negative voltage, 0 to say minus 5 volts. You can vary minus 1 volts, minus 2 volts. When to gate only if you change, more number of holes will be attracted, channel with more current will flow. By controlling a negative voltage applied to gate terminal, which is called VGS, will vary from 0 to minus 4 or minus 10 volts. For given MOSFET, the manufacturer says, like VBE, VBB max, VCC max, like this, they will give. If I vary that and give the supply voltage like this, then current flow can be ID, yes, can be controlled. This is for main thing. Here the P substrate, N channel form. If it is N substrate, P channel is formed. The pools are positive, heavily doped, positive, heavily doped. Here, negatively heavily doped, negatively heavily doped. Okay, we can see that. Okay, so P channel, again, input output characteristics I have shown. Now, we will see N-channel MOSFET in depletion mode, correct? So N-channel, again, N-channel means P substrate, correct? Whether it is a depletion mode operation or enhancement mode, if my MOSFET N-channel, the main substrate is P-type material, on which two wells are dug, filled with N-type material or N plus material, heavily doped this one. So one will become a source, other one will become a drain. Across that, I supply a voltage VDS, some books VDD. I told you in the transistor they put VCE or plus VCC. Same way here also. Okay. In MOSFET, some books they put VDS, in some book they put VDD. Drain is connected. That is main power supply. Correct? This is main power supply connected. Then I have connected my gate terminal to source, short circuited. Please see here, the gate terminal connected. That means, what is gate terminal? This is 0 volts. This is positive. So that means my gate voltage VGS equal to 0. Okay. And main thing what you have to see here, Chidambaram has nicely asked at the beginning of the class itself. Correct. So if it is a depletion type MOSFET, whether N channel or P channel, already channel will be there. You can see the channel feed fabricated by manufacturer with electron filled, partially filled. Okay, you have a particular thickness of channel through which current can flow. If I give VDD without giving gate voltage, my VGS equal to 0 because I connected to ground. Okay, and I supplied positive voltage to drain. For example, this is 100 volts and negative voltage connected to source. Now, if I go and see that this is my ID, correct? If I measure ID may be 10 amps current going. or 15 amps current going. Manufacturer decides. That depends upon this width of the channel. Free-formed width. Okay. Free-formed width with the electrons. Okay. Now, if I wanted to, now, then how I'll control? That means the main beauty of the depletion mode operation is for 0 VGS, gate control voltage, there will be a current flowing through your load. Some occasion you want that, correct? I want always, for example, I have, I will say that this is my load, RL. I want some current should be flow. So 10 amps current always will flow. Then I want to increase the current or decrease the current to 0 amps or increase the current to 20 amps. Normally, the load current to be 10 amps should go. And by giving a control voltage VGS, gate control, I want to increase or decrease from 10 to 9, 8, 0 or 11, 12, 13. If I want to do that, what will be the best thing is use depletion mode MOSFET. Okay. So it has a feedback with it. Again, you have to give a power supply between VDS between drain and source, and you have to give control voltage. Now the control is given. So that's the current is going. Now I wanted to reduce the current. Correct? I want to reduce the current from 10 amps this one. What did you do? Already my source voltage given. Between drain I give a negative voltage. See here VGS equal to -1 volt. Here my VGS equal to 0 volts. Because I connected my gate to 0 volts, correct, of the power supply. Now, I am introducing already my power supply is the main power supply, which is connecting this through my load RL. This is plus minus. This is my VDS or VDD. That's there. I introducing control VGS. But what I'm giving? A -1. Please, a negative terminal is connected. So -1 volts I'm giving. Once I give negative this one, what will happen? What is the material? P material. Correct? What are the majority carrier? Holes. More holes are there, but few electrons are there. Here and there. Correct? When I go to enhancement mode, if I give a positive voltage to my gate of the N channel, this will be attracted. Because initially there is no electrons, they attract and form a channel. That is the enhancement mode operation. Minority carriers to be attracted. If I give positive voltage to gate in N-channel MOSFET. Now, what I am giving? A negative voltage I am giving. If I give negative voltage, what will happen? There are positive holes in the P material. They will be attracted. Because a negative voltage will give a negative. Because again, this is a capacitor. Please see that a capacitor. I give negative voltage, electrons will charge. So electric field is created. Negative electric field is created on the gate side of the metal. There's an insulator. And positive side, what will happen? This will attract positive electrons from here. Holes from this one. They come and form a layer. You can see here. Once I gave the negative voltage, initially I gave 0. Now I gave positive voltage. What happened? The holes in the P material, which is a majority carrier, come and attract a form a layer. Okay. Once they come near, what will happen? There's a negative electron already pre-channel, and this one, they join together, they recombine. Correct? Electron hole will join, they neutralize. So this region become neutral. That means one set of electrons has combined with the positive. So what it means? My thickness of the layer is reduced. Correct? So one set of layer of electrons combined with holes, they become neutral. Correct? That means this is my channel width. Correct? This is my channel width. So originally this was my channel width. 2 electron thickness. Now I have 1 electron thickness only. My channel width is reduced. Correct? So what will the channel width means? My IDD. Correct? Load and power supply. This is my current ID. ID will reduce. If I give more negative, correct? ID will still reduce further. So that's why the depleting means removing, depriving. That is what depleting. What I'm doing by giving negative voltage to my gate terminal of a depletion mode N channel, I am reducing number of electrons available by recombination. So the width of the channel reduces. More and give. At one stage, all electrons will become more positive will come. The channel will disappear. If I give, for example, VG is equal to -5 volts for the particular MOSFET, my thickness, correct? I say that TW or width, correct? Width of the channel, I can say that will become 0. That means my IDS will become 0. Okay. So instead of that, if I give positive voltage, another beauty of the depletion type of this one is, if I give a positive voltage, it will work like an enhancement mode. If I give a negative voltage, it works like a depletion mode. That means with this one MOSFET, I will be able to control positive and negative with respect to base current. Please note that base current cannot be 0 in case of depletion MOSFET, because already pre-existing channel. The width can be increased or decreased. If I give a positive voltage, what will happen? Positive charge appears on the top side. Here what happened? Here we got it. If I apply negative voltage, negative will reach. Because of that, the holes were attracted. Width was reducing. In this case, if I give a VGS is positive, then positive charge field, electric field is created on top of the gate terminal capacitor. So electrons are attracted. Minority carrier, you can see the new fresh carrier has coming. So my width of the channel has tripled from original to more current flows. Correct? Current from 10 amps will become 11 amps. If I give +1 volt, if I give +2 volts, it will become 12 amps. So like this, you can vary. So you can see here, finally, I want to close this. You can see here, this is the input-output characteristic of the N-channel depletion mode MOSFET. Okay? You can see here, I gave VGS equals 0, there's a current going. Right? It's not 0. When VGS is 0 in the enhancement mode MOSFET, ID was 0. But in case of depletion, you can see it's not 0. It may be something decided by the manufacturer. For example, you say 10 amps, 50 amps, depending upon data should LCD. If I give more negative, from 0 increasing my negative side, you can see the current is reducing. 8 amps. Correct? If I give -2, it becomes 6 amps. I give -3, 4 amps. If I give -4, 0 amps. If I increase negative voltage applied to depletion type N-channel MOSFET, the ID reduces, load current reduces. Instead of that, if I give a positive voltage, I give one more, it has from 8 volts, it comes to, say for example, 12 amps or 13 amps. If I give still more, it may go more. So using depletion type, this one, I can operate as a depletion mode, also as an enhancement mode. But only drawback is, in enhancement, pure enhancement MOSFET, the for VGS equals 0, the ID will be 0. Here it is not, load current can be made 0. Okay. So again, just 2 more slides. I want to complete this. P-channel MOSFET in depletion. We saw N-channel MOSFET, correct? Depletion mode, enhancement mode, all those things we saw. Lastly, we are seeing P-channel in depletion mode. Again, P-channel means in MOSFET, the base material, or they call a substrate. This is another name they use. Base or substrate material is N material, and there are 2 pools of P. One will become a source, other will drain, and there's an insulation layer on which metal contact, that is your gate, and you have to give a negative voltage to drain, positive voltage to source in P channel, and a positive voltage can be applied or negative voltage can be applied as a gate control. Again, you can see here, correct? So this is this one control voltage VGS, positive or negative. Accordingly, the ID can vary. Please see that in depletion means whether N channel, P channel, for 0 volts, there will be some current. ID will be there. You cannot stop it. It can be increased or decreased. If I give positive voltage, this will decrease. If I give negative voltage, it will increase. Reverse of N channel MOSFET. Okay. Finally, this what we showed. Drain input character already explained. Thank you very much. So next Monday, we'll start the battery, right? Energy storage devices. We'll talk about lead acid battery, lithium ion battery, how they are working. These are 2 important battery used in electric hybrid automotive. This one, other type battery, we are not going to talk about it. In fact, lead acids are now become only for, not for driving the motors, correct? Lead acid battery generally 12 volt, 24 volt, now 48. But lithium ion battery 600 volt pack, 400 volt, high voltage, all this thing is better. We'll see why lithium is better than lead acid, many advantages. Then we also see about supercapacitors. Correct. Batteries have a lot of drawbacks. To avoid that, nowadays they're coming with supercapacitor, which can be used as a battery to drive your electric motor. We'll see how it works. Maybe 3 to 4 classes. Afterwards, we'll just see about the calculations about what we call the configurations, motor power, torque requirement, the different series parallel, series semi-parallel, all this thing we'll see 5 to 6 classes. Okay, we'll complete that. Thank you very much. See you on Monday. Have a nice weekend.
So, sir,
Happy Friday, this one, Good Friday.
sure,
Friday.
happy weekend, sir. Sir, maybe like we will discuss next week, sir, some basic query, like as for me, actually, like I'm as a mechanical engineer. But we can discuss it on Monday, sir. Like this is about this power electronics. Some of the devices are current controlled devices, and some of them are voltage controlled devices.
Voltage control.
So
Yeah. Please tell me.
Yeah, but means if we apply voltage to any wire, the current also will vary. Why there is a difference between these two actually, like in these devices?
Just 2 minutes, if you don't mind. Now it's will explain. Correct?
Okay, sure, sir. Sure.
Yeah. For example, I have a battery. Correct? 10 volt battery. Okay. Battery, if you take any battery terminal, you may connect a voltmeter. Correct? It shows whatever voltage is already. Voltmeter shows this one. Now we say the circuit is open. It is called an open circuit. Battery is not connected to open circuit. Battery is not connected to any load. Now, what I did, I connected to a resistor. I say our load resistance, 10 ohms. Correct? 10 ohm load resistance. Now, once I connect a load between positive and negative terminal of the energy source, which is a battery 10 volts, automatically we say the circuit is closed. Correct? Once circuit is closed, automatically current from positive terminal will flow through this one, complete. So current flows, I flows. Okay? This I call V equal 10 volts. My load, because I connected load across this one voltage source, definitely current has to flow according to Ohm's law. Correct? Ohm's law is a person who invented this concept of electricity current relationship. Okay, so what it says, I equal to V by R, where V is the input, I is the output. This is the output, this is my input. R is the property of the circuit, correct? Which is nothing but resistance. Okay, so input divided by resistance is going to give the current. This is okay. Okay, now we talked about 2 devices. Okay, one I talk as transistor. That's why we come into picture. Correct? We come into picture. One is transistor, collector, emitter, base. I am talking about NPN transistor. Okay. Now we know that the transistor equivalent circuit. Anybody remember? This is R in, this is R naught, this is current source, beta times IB. Okay, so here I give my input voltage, and here I connect my load. So this is my collector terminal, this is my emitter terminal, this is my base terminal. So this is my base terminal. Okay, so now I give input 10 volts or 5 volts. This is called VB. What is IB? IB equal to, this is nothing but RB. Okay. VB divided by RB. This is the input current flowing. This current is entering into the transistor. Then that will be multiplied by beta times, correct? and my IC will become IB into beta. Beta already manufactured to 100, 200, 1000, whatever may be. So if I give a current, because there's a circuit is closed. Please see here, this is a circuit having one resistor, one current source, another resistor. This is my external load resistor, forget it. So I give an input voltage and it is applied to a resistor and the circuit is closed. So automatically there's a current has to flow. Correct? Current is flow. Okay. How much current flows? That depend upon this resistance RB value. Correct? I give my input voltage is VB. I can give 0 volts or 1 volt, 2 volt, 3 volt or whatever voltage is allowed. I say for example this is 5 volts for this particular transistor. So that means maximum VB can be 5 volts. Okay. The RB internal resistance or R in of the transistor is called dynamic. This one that is decided by the manufacturer of the transistor. He says it is 10 kilo ohms. Okay, that means if I give 5 volts and my R internal resistance or base resistance of the transistor inside is 10 kilo ohms, my IB is going to be 5 divided by 10 into 10 power 3. Correct? We can say that 5 into 10 power minus 1, which is going to be this much current flowing. Now, already I told, if I connect, what for the transistor amplifier is used? This amplifier, transistor amplifier I'm using. I have a sensor, correct? I have V sensor, for example, thermocouple, which gives, here I said 5 volts. For example, sensor, how much volt? A strain gauge bit, 0 to 100 millivolts or 0 to 500 millivolts. This needs to be amplified. And for that only I'm using a transistor amplifier. And I'm giving VCC, plus minus, IC. IC will be amplified version of IB. IB depends on input voltage. But if I take some current from my sensor, already told loading effect comes into picture, correct? And how will you reduce loading effect? That means you need a transistor whose R in or base internal resistance is very high. Okay, that is what. But whatever the transistor make, the internal resistance, if you increase, the amount of current goes in, then you need to make transistor gain beta. But I want IC to be bigger. IC should be bigger than IB. That means I want IB should be less. If IB has to be less, RBE or R internal resistance should be very high, correct? If I make it, then beta should be very high. Okay, but we know that transistor beta, if you go on increase, thermal drift. Do you remember last time I talked about in mechatronics? Beta, when we talk about op-amp, why it was op-amp was invented? Beta of the transistor is not constant. It is temperature different. If transistor amplifier is at 0 degree, correct? Morning in America, winter, it gain equal 100. You bring it to Sahara Desert, 50 degree, correct? The gain will not be 100, it will be 110. Correct? For example, you are driving from Chennai to some place or Ooty. As your car has internal some transistor amplifiers, and Chennai temperature very high. If you go to Ooty, it is 10 degree. Chennai 38 degree. Gain will change. Your control will not work properly. That's why they invented op-amp and also gave negative feedback, which eliminates the open loop gain. AOL is automatically removed because of feedback gain controls. If you remember all those things. These are things they had done previously. Then what they did is, transistor is not good enough. Instead of that, they invented what you call a MOSFET. Correct? MOSFET, already we saw that it is like this. Source, drain, gate. This is a MOSFET, correct? In the MOSFET, gate, we saw just now we saw. What is there here? The MOSFETs. I am giving input voltage to the gate, and in between there is an insulator. The resistance of this is 10 power 9 to 10 power minus plus 12. Okay, he gave 1 volt. Current, how will you go? From here, it has to go through the insulator and reach the P. In transistor base, directly happens. There's the insulator is not there. So automatically current goes inside this because of the low impedance. Now, since my silicon SiO2, which is called insulator, is there, his resistance is very high. I say Ig, gate current, equal to VGS divided by Zin or Rin of MOSFET. Rin of the MOSFET automatically include this number. So I say that if my input is 5 volts, my Zin, because of the insulating layer of the MOSFET, whose resistance is 10 power 9 to 10 power 12, theoretically, this should be infinity. The resistance of the silicon layer, insulator, should be infinity. Impossible to make pure silicon dioxide. Humans don't have the capability except God. As a human, there will be some impurities. That means his insulation will not be resistant, will not be infinity. It will be in the 10 power 9, 10 power 12. Or 12 this one. So that means 5 divided by 10 power 10, you take it easy. Okay. What it means is 5 into 10 power minus 10 amps, which is nothing but 0.9 nanoamps or 900 picoamps. Ig. Can you think this is equal to 0? That means if I use the MOSFET, whatever, it doesn't take current. But if I vary my VGS, my ID is varying. My VGS varies 0 to 5 volt. ID can vary by increasing the width of the channel width control, and IDS can vary by hundreds of amps. So that's why this is called a voltage control amplifier. Why? Basically, it consumes some current. Please see that depending on the input impedance of the MOSFET, which is 10 power 9, 10 power 8, 10 power 10. Correct. Some amount of current, nanoamps or picoamps current are going, that can be considered close to 0. Right? That's why we say it is voltage operated device. Literally speaking, it is also there's some current. That current is so small, you can neglect it. So that means if I vary my input voltage 0 to gate voltage 0 to 5 volts, my drain current will 0 to 100 amps will varies without taking any gate current. That's why it is called a voltage operated. FET and MOSFET and IGBT. IGBT, what is in the first stage? MOSFET. MOSFET output is given to transistor. Yesterday only we saw. Correct? That's how it works. Thank you very much.
Yes. Okay. Sure, sir. Thank you, sir. So my understanding is wherever the input impedance or like input resistance is high, we say it as a voltage controlled devices.
Yes,
and
that means MOSFETs. FET and MOSFETs have very high input impedance compared to transistor. If you are using transistor amplifier, if the input resistance is 100 kilo ohms, the JFET, the input impedance is 1 megohm, 10 times more. Okay. Instead of that, if I use MOSFET, it will be 10 mega ohms, 100 times more compared to transistor. So virtually it is consuming some current, but it's very, very negligible. So that's why we call it voltage control amplifiers.
Okay, sir. Sure.
Including
Thanks
IGBT.
for the clarification, sir.
Okay.
Yeah, sure.
Thank you.
Thanks for the clarification, sir. Thank you.
Yeah. Thank you very much. See you on Monday. Enjoy your 3-day long weekend carefully, safely.
Thank you, sir.
Okay.
Thank
Take
you.
care.
Thank
Okay.
you, sir.
Thank you. Give your attendance before leaving because